Imagine a clock, not just any clock, but one that spans billions of years. Each tick resonates with the echoes of cosmic events, marking epochs in the universe's grand narrative. We begin at the beginning, a point infinitesimally small, incredibly dense, and unimaginably hot. This is the singularity, the seed of the universe as we know it. Time starts, space expands, the universe is born in a fiery explosion, the Big Bang. In a fraction of a second, the universe undergoes a period of rapid inflation, expanding faster than the speed of light. This cosmic expansion continues today, though at a more leisurely pace. The early universe is a chaotic soup of fundamental particles, quarks, leptons, and bosons colliding at unimaginable speeds. As the universe expands and cools, these particles begin to coalesce, forming the building blocks of matter as we know it. The universe is a vast and mysterious place, and its origins remain one of the most profound mysteries in science. The universe, once a blindingly bright inferno, begins to cool. Light, trapped within the dense particle soup, breaks free, illuminating the cosmos for the first time. This afterglow of the Big Bang, known as the cosmic microwave background radiation, still permeates the universe today, a faint whisper of creation. Around 380,000 years after the Big Bang, the universe has cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. This event, known as recombination, marks a pivotal moment in cosmic history. The universe transitions from being opaque to transparent, allowing light to travel freely across vast distances. With the formation of neutral hydrogen, the stage is set for the emergence of the first stars. Gravity, the architect of the cosmos, begins to draw together clumps of hydrogen and helium gas, gradually increasing their density and temperature. These dense clouds of gas, known as nebulae, will become the stellar nurseries of the universe. Deep within the swirling clouds of gas and dust, gravity exerts its relentless pull. As the density of these clouds increases, so too does their temperature. The hydrogen atoms, once separate, are drawn closer and closer together, colliding with ever-increasing force. At the heart of these collapsing clouds, a protostar is born. A protostar is a celestial object in its infancy, a ball of hot, dense gas that is still contracting under its own gravity. As the protostar continues to contract, the temperature and pressure at its core continue to rise until a critical threshold is reached. At this point, a process known as nuclear fusion ignites, releasing an immense amount of energy and marking the birth of a star. The first stars, much larger and hotter than our own sun, blaze with incredible intensity, flooding the surrounding space with ultraviolet radiation. These stellar pioneers play a crucial role in the evolution of the universe, synthesizing heavier elements within their cores through nuclear fusion. These heavier elements, such as carbon, oxygen, and nitrogen, will eventually become the building blocks of planets and life itself. Across the vast canvas of the cosmos, a grand ballet unfolds. Galaxies, vast islands of stars, gas, and dust begin to take shape. Driven by gravity, these massive structures engage in a delicate dance, sometimes colliding in spectacular mergers that trigger intense bursts of star formation. These cosmic collisions, while seemingly destructive, actually play a crucial role in the evolution of galaxies, shaping their morphology and driving the formation of new stars and planetary systems. Spiral galaxies, like our own Milky Way, exhibit graceful arms adorned with bright young stars and glowing nebulae. These galactic spirals are thought to be sculpted by density waves that propagate through the galactic disk, triggering star formation as they travel. Elliptical galaxies, in contrast, appear as smooth, featureless ovals, populated by older, redder stars. These galactic behemoths are often found at the centers of galaxy clusters, suggesting that they may have formed through the mergers of smaller galaxies. Over billions of years, galaxies evolve and interact, their graceful movements weaving the intricate tapestry of the cosmos. The universe, once a sea of darkness punctuated by the light of the first stars, is now ablaze with the brilliance of trillions of stars, clustered together in a vast cosmic web of galaxies. In a quiet corner of the Milky Way, a swirling cloud of gas and dust begins to collapse under its own gravity. This particular cloud, unremarkable in its size and composition, will eventually give rise to our solar system, the sun, the planets, and ultimately, life itself. As the cloud collapses, it begins to rotate, forming a flattened disk of material around a central protostar. Within this disk, dust grains collide and stick together, gradually accreting into larger and larger objects. Over millions of years, these planetesimals, as they are known, coalesce to form the familiar planets of our solar system. Closer to the Sun, where temperatures are higher, rocky planets with solid surfaces form: Mercury, Venus, Earth, and Mars. Farther out, where temperatures are colder, gas giants, Jupiter, Saturn, Uranus, and Neptune, accrete massive atmospheres of hydrogen and helium. And in the outermost reaches of the solar system, beyond the orbit of Neptune, lies the Kuiper Belt, a region populated by icy bodies, remnants from the early solar system. On a young Earth, still reeling from its fiery birth, the conditions for life as we know it are harsh and unforgiving. Volcanoes spew molten rock and noxious gases into the atmosphere, while comets and asteroids bombard the planet's surface. Yet amidst this chaos, the seeds of life take root. In the primordial oceans, a remarkable transformation occurs. Simple organic molecules, formed through a combination of chemical reactions and energy from the sun, begin to self-assemble into more complex structures. These structures, known as protocells, exhibit some of the basic properties of life, such as metabolism and reproduction. Over millions of years, these protocells evolve and diversify, giving rise to the first single-celled organisms. These early life forms, known as prokaryotes, lack a nucleus and other membrane-bound organelles, but they possess the remarkable ability to harness energy from their environment and replicate themselves. Life, once a fragile spark, has taken hold on Earth, forever altering the trajectory of this pale blue dot. Life on Earth undergoes a profound transformation with the evolution of photosynthesis. Cyanobacteria, also known as blue-green algae, develop the ability to capture sunlight and convert it into chemical energy, releasing oxygen as a byproduct. This process, known as photosynthesis, gradually transforms the Earth's atmosphere, paving the way for the evolution of more complex life forms. As oxygen levels rise, a new type of organism emerges: eukaryotes. Eukaryotic cells, characterized by their membrane-bound nucleus and other organelles, are larger and more complex than their prokaryotic counterparts. The evolution of eukaryotes marks a major leap forward in the complexity of life on Earth, setting the stage for the emergence of multicellular organisms. From the first simple, single-celled organisms to the incredible diversity of plants and animals we see today, life on Earth has been shaped by a relentless process of evolution. Natural selection, the driving force behind evolution, favors organisms that are best adapted to their environment. Over countless generations, this process has given rise to the astounding array of life that inhabits our planet, from the towering redwoods to the microscopic bacteria that teem within our own bodies. As we shift our gaze back to the grand cosmic scale, we encounter a universe far more vast and intricate than we could have imagined. Galaxies, once thought to be isolated islands in the cosmos, are revealed to be interconnected by a vast cosmic web of filaments and voids. These filaments, composed of galaxies, gas, and dark matter, stretch across billions of light-years, tracing the underlying structure of the universe. At the intersections of these filaments lie galaxy clusters, the largest gravitationally bound structures in the universe. These clusters, containing hundreds or even thousands of galaxies, are cosmic metropolises, teeming with activity. The cosmic web is a testament to the power of gravity, which has sculpted the universe into its present form. The distribution of galaxies and galaxy clusters reflects the initial conditions of the universe, shortly after the Big Bang. By studying the cosmic web, astronomers hope to unravel the mysteries of the universe's origins and evolution. Our exploration of the universe has led us to a profound realization. Most of the universe is invisible. Observations of galaxies and galaxy clusters suggest that there is far more mass present than we can account for with our current understanding of physics. This missing mass has been dubbed dark matter. Dark matter does not interact with light or other forms of electromagnetic radiation, making it invisible to our telescopes. However, its gravitational influence can be inferred from its effects on the motion of visible matter. The nature of dark matter remains one of the greatest mysteries in modern astrophysics. Adding to the cosmic puzzle, scientists have discovered that the expansion of the universe is accelerating. This unexpected finding suggests that there is another, even more mysterious component to the universe: dark energy. Dark energy is thought to be a repulsive force that counteracts gravity, driving the accelerated expansion of the universe. Together, dark matter and dark energy account for approximately 95% of the total mass energy content of the universe, leaving ordinary matter, the stuff of stars, planets, and life, as a mere cosmic afterthought. The vastness and diversity of the universe beg the question, are we alone? The search for extraterrestrial life, once the realm of science fiction, has become an active area of scientific inquiry. Astronomers are now discovering planets around other stars, known as exoplanets, at an astonishing rate. Many of these exoplanets reside in the so-called habitable zone around their host stars, where temperatures are suitable for liquid water to exist on their surfaces. Liquid water is considered an essential ingredient for life as we know it, so the discovery of potentially habitable exoplanets has fueled speculation about the possibility of extraterrestrial life. While we have yet to find definitive evidence of life beyond Earth, the search is ongoing. From the icy moons of our solar system to the distant exoplanets orbiting other stars, the universe holds endless possibilities for the existence of life. The discovery of extraterrestrial life, even in its simplest form, would have profound implications for our understanding of our place in the cosmos. Our journey through the universe has taken us from the Big Bang to the present day. From the smallest subatomic particles to the largest cosmic structures. We have witnessed the birth and death of stars, the formation of galaxies, and the emergence of life on at least one planet. As we stand at the precipice of the unknown, we are reminded that the universe is a place of endless wonder and possibility. New discoveries are constantly reshaping our understanding of the cosmos, revealing a universe far more complex and awe-inspiring than we could have ever imagined. The universe is a vast and mysterious place, and we are just beginning to explore its secrets. The journey ahead promises to be filled with challenges and surprises, but it is a journey that we must undertake if we are to fully comprehend our place in the grand scheme of things. The universe beckons, inviting us to continue our exploration of its boundless wonders.